In this video, we're going to extend our counting techniques to discuss permutations and combinations. So these are going to be two specific situations that involve counting where we have some specific requirements on how we're counting. So a permutation of a set of n distinct objects is an arrangement of the objects in a distinct order without repetition. In other words, we have a set of items, all we are doing is arranging them where the order we put them in does matter. So each time we use an object in the set, we can't use it again. We're just taking a collection of items and putting them in order. So maybe think about ranging things alphabetically or Z to A, something like that. Each of those would be considered a different permutation. So we're taking a collection of objects, just putting them in order. Now, sometimes we won't want to arrange the whole set. Maybe we have a set to choose from, and we just want to take a subset of that and then arrange the elements in the subset. In a lot of situations, that's what we're going to do. So if we have n objects to choose from, in other words, that's the bigger set, and we're taking a permutation of r of these objects. In other words, we're taking a smaller selection from the bigger set and then just arranging that smaller selection. Then our permutation notation is given by NPR. So big P for permutation. N is going to be the number of items we have to choose from. So it's going to be the bigger set. R is how many items we're choosing. So maybe we have a class of 32 people and we're choosing 5 to go represent the class somewhere. N would be 32 and R would be 5 in a situation like this. So there's a formal way of defining what this actually represents in terms of actual mathematical operations, but we're going to use an operation on the graphing calculator for calculating the number of permutations. So it's going to be under the math menu and then the probability submenu, and then we're looking for NPR. So once we get to some actual numbers, I'll show you how to find those particular operations. We have another one. In addition to permutations, we can also take what we call a combination. It's similar with one distinct difference. So a combination of a set of n distinct objects taken r at a time. So now we're just looking at subsets. We're not taking the whole group, we're just looking at subsets. We're going without repetition again, so once we choose an item, we can't choose it again. It's just a subset. In this case, the order does not matter. So think of a combination like a one-step process, and think of taking a permutation like a two-step process. For a combination, we have a set of n items, and all we're caring about is finding a subset. We just want to find a subset of it, no repeats, take a subset, and then just have a subset. The order we put the items in does not matter. So if we were to take any particular subset and rearrange all the items in it, it's still the same thing, it's still the same subset, it's still the same combination. Now if we're taking a permutation, very, very similar with one distinct difference. We're taking a subset, so we have n items to choose from, and we're taking a subset of r, but then we're taking a second step and we're also arranging the items. So any particular subset, we then have to arrange. So one subset but arranged in a different order is considered different if we're talking about a permutation. So the biggest things to remember: a combination, the order doesn't matter. A permutation, the order does matter. We're going to use these two concepts in counting situations, and determining which situation we're in is always going to be where we start. If we're talking about a combination, we're talking about a situation where the order doesn't matter. Rearranging things doesn't change the situation we're in. If we're talking about a permutation, then we're talking about a situation where rearrangement does change the situation we're in. So just like with a permutation, we can find a combination button on the graphing calculator. Same location, math, probability, but now it's going to be in CR. So C for combination, N is the total number of items we have to choose from, and then R is how many items out of that group we want to choose. So I want to look at some applications. We're just going to do a bunch of examples. This is the kind of section where you just need to do examples. And again, there's always going to be steps in the process. So we always have to start by determining, are we looking at a permutation? Are we looking at a combination? Does order matter or does order not matter? So here's our example. A preschool teacher wants to create a seating chart for her type of for a class of 10 students. how many different arrangements are possible. Okay, now she's arranging the students. She's creating a seating chart. So in this case, there is very much an implied order. Maybe she arranges the kids in alphabetical order. Maybe she arranges them reverse alphabetically. Maybe it's alphabetical by last name. Maybe it's alphabetical by first name. Maybe she alternates boy, girl, boy, girl. Maybe she puts all the girls on one side, all the boys on the other side. Any situation, the rearrangements create a different situation. So this would be a permutation problem because there's an implied order involved in this situation. Now, once we know that it's a permutation problem, we then have to determine what's N and what's R. N is the number of items we have to choose from, and R is going to be how many of those items we're actually taking and in this case arranging. Well, she has a class of 10 students, so she has 10 to choose from. N definitely has to be 10. Now she's going to take the whole class and arrange them. She's not necessarily saying these students have to work in a group, these students have to work in a group. She wants to arrange the whole class. So N is 10, but R is also 10 because she's arranging the whole group. So it's going to be 10 permutation 10. Now, where do you find this on the graphing calculator? Let's look at that. You're going to use the math menu, but I want to preface this by just pointing out that there's going to be sort of two versions of how you type this in. It's going to depend on how new or how old your calculator is. So my calculator is pretty new, which means I'm going to go directly into the math menu and I'm going to find that permutation operation. Let me go in and show you where it is, and then I'll explain the difference between how you might do this versus how I do this. So I'm going to go to the math menu. I'm going to go to the prob submenu. So prob stands for probability. So I'm just going to scroll over using my arrows to probability. And notice your second option is NPR. And then right below that, there's NCR. So that's going to be permutation and then combination. This is a permutation problem. So I'm going to scroll down and I'm going to hit enter. Now notice with my calculator, it entered that format, but it also has little boxes that are going to allow me to type in my values for N and R. So my value for N is 10. It fills that into the box, and then I can arrow over if I then want to type in R, which is also 10 in this case. Now your calculator may not do this. If you go and you choose the permutation operation from the math menu and you don't actually have little boxes right there, it might just say NPR and not actually have boxes, actually have an N and actually have an R. If that's the case, then you're going to have to type things in slightly differently. Rather than choosing the permutation operation first, you're going to type your N first, then you're going to go into the menu and find the permutation operation. You're going to highlight that, select it, hit enter. That'll bring you back to the home row. So you'll have your N, then you'll have your permutation operation, and then you'll type the R after that. So if your calculator is a little old, you're going to have to type it that way. So just look at yours, explore a little bit about what yours is doing. If you type that operation and you have those boxes to type into, then you can do it this way. Otherwise, you need to type N, then go get the operation, and then type R. So in this case, regardless, 10 permutation 10, we take that and that's going to be this number. How do you know how this is or what size this is? We get a lot of big numbers in these problems, which are surprisingly large. Start by counting from the right, so count by threes. So threes, and then we have another 3. So this is going to be 3 million. So 3,628,800. This is, believe it or not, how many different arrangements she can make for her class. If she arranges all those 10 students, believe it or not, there's over 3 million ways to arrange 10 students. If you don't believe something like that, well, maybe don't worry about arranging students. Maybe just take the first 10 letters of the alphabet and start making lists of arrangements. You'll find pretty quickly that the numbers get really, really big. There's a lot of ways to arrange. You can do alphabetical, you can do reverse alphabetical, and then any combination in between is also considered a different permutation. So believe it or not, there's actually a lot of ways to arrange, even though we're only looking at 10 items to arrange. Okay, let's look at some more examples. From a committee of 10 people, we have 2 questions. Question 1, In how many ways can we choose a chairperson, a vice chairperson, and a secretary, assuming that each person can hold at most one position? Now, there's not specifically an order here, but notice that there's a hierarchy. We're assigning specific roles. We're not saying that everyone is even and we're just taking a set of people. We're taking a subset of 3, so we're assigning 3 roles out of the 10 we have to choose from. But notice the roles are very specific. So if you were to think of maybe 3 seats at the table, the first seat is for the chairperson, the second for the vice chairperson, and the third for the secretary. The order you sit people in at the table determines their role. So any group of 3 people, if you then rearrange the 3 people, you have a different officer's assignment. So in that case, this is going to be a permutation problem because there is some type of ordering involved, even though it's not ordering in the same way that we're arranging a seating chart, something like that. But there is an order, so this is going to be a permutation. Now we have 10 items to choose from, and because we have 3 officer positions to assign, we're choosing 3 out of the 10. So this is going to be 10 permutation 3. So let's go back in and let's do that one again. So 10, go to the math menu, probability. This is what it's going to look like if you have to do it the other way. Now notice mine's pretty smart. I typed the 10 and I went and got permutation, and it automatically put the 10 in the box. So if you want to do it that way, that's fine as well. And then we have our 3. I'm going to hit enter and we get 720. So 720 different ways to choose officers based on choosing 3 officers out of a group of 10. Now let's tweak the situation slightly, change the situation just a little bit and see what the difference is. So here's the next question. In how many ways can we choose a subcommittee of 3 people? How is this different from the question above? Well, in the question above, we had specific roles to assign. Someone is in charge, someone is the vice person in charge, and then there's a secretary. So there were specific roles. In other words, there was an implied ordering. Now, if we're just choosing a subcommittee, we're just choosing 3 people to work together. It doesn't matter where they sit at the table. We can rearrange them, and it's still the same subcommittee of people. So this situation actually represents a combination. Since the order we choose them in and arrange them in doesn't change the outcome, this is a combination situation. So assigning specific roles is a permutation. Just choosing a collection of people is going to be a combination. Now, N and R have not changed. We still have 10 people to choose from, and we're still choosing 3 out of the 10. What's changed is now it's a combination instead of a permutation. So if we go into the math menu, probability, we're choosing combination, which is right under permutation. So combination. And then I have 10 to choose from, and I'm choosing 3. And there's going to be 120 combinations. In general, all other things the same. If N and R are the same, there's always going to be more permutations than there are combinations. Combinations get rid of a lot of the possibilities. Taking one group of 3 and then rearranging it, we don't have any differences. Whereas if we're talking about a permutation, any particular group of 3 but rearranged represents a different possible outcome. So in general, the number of permutations we find is typically going to be substantially higher than the number of combinations we find. Okay, so that's just a couple of basic examples. We're going to build on there. There are a lot of different situations where we can use permutations and use combinations. And we're just going to practice identifying the situations and figuring out what N and R are, breaking the situations down into pieces. Particularly as the situations get more complicated, we're going to find we have to use not only permutations and combinations, but also the multiplication principle that we talked about in the last video. So remember, when we want to perform a sequence of steps, a sequence of operations, we can do each step a certain number of ways, and then we multiply those number of ways together. Well, what happens if each individual step represents a permutation or a combination? We can have little problems nested inside of bigger problems. So that's what we're going to look at next. Now, playing card problems are always a good option for modeling these situations because they're very visual. If you don't know too much about cards, you don't play cards on a regular basis, you may want to grab a deck of cards just so you have it available, so you have something visual. So just to explain in general what's in the pack of cards so we know we're on the same page. So we have 4 suits in the deck. We have 2 black suits, 2 red suits. So the black suits are going to be spades and clubs, and then the red suits are going to be hearts and diamonds. Each suit has 13 cards. So if you think of starting with an ace, we have aces through 10s. Those are going to be non-face card, non-picture cards. And then the jack, the queen, and the king for each suit, those are considered to be face cards or picture cards. So 13 of the same cards per suit. So 4 suits, 13 cards per suit. So we have a total of 52 cards. This, of course, is assuming we remove the jokers or any additional cards we have in the deck. So just aces through kings for each of our 4 suits. Okay, so here is a question with regards to playing cards. We want to know how many 5-card hands have 3 aces and 2 kings. Well, we need to start by determining, are we looking at a permutation situation or a combination situation? Does the order we get the cards in matter? So picture dealing 5 cards out, and then you pick up all your cards at one time. Maybe you're playing poker. You get a pretty good hand, 3 aces and 2 kings. Okay, but does the order the hand comes in matter? The answer to that is no. When you pick up the cards, you can rearrange the cards in your hand and it's still the same 5-card hand. Rearranging the order of the cards doesn't actually change anything in this situation. So this is going to be a combination rather than a permutation. Now this is a combination, but there's a little bit more to it than just choosing 3 people out of 10 or choosing 5 cards out of our deck of cards. Notice we have specific requirements for the cards that have been chosen. We want to specifically get 3 aces and 2 kings. I want you to think about guaranteeing. How would you have to stack the deck, for lack of a better way to put it? How would you have to stack the deck so that you know that you get 3 aces and you know that you get 2 kings? The only way you could guarantee that you're specifically going to get 3 aces and specifically get 2 kings is to throw away all the other cards in the deck. If you're dealing from the whole deck and it's fully shuffled and everything is essentially random, there's no way you're going to guarantee that you don't get all number cards as opposed to these particular cards. How do you guarantee you only get aces and kings? Well, you have to, number 1, throw away all the other cards, but number 2, you would also have to deal your 3 aces individually just from the set of aces, and you'd have to deal your 2 kings by themselves just from the set of kings. Well, how many aces and kings are there? Well, there's 4 aces in the deck, there's 4 kings in the deck. So essentially what's happening is we're choosing a total of 5 cards, but we're choosing these particular kinds of cards just out of the set of aces and then just out of the set of kings. So this is actually a 2-step operation. Operation 1 is choosing our 3 aces, and then operation 2 is choosing our 2 kings. Well, how many ways can we choose 3 aces? This is in itself a little combination problem. We're choosing 3 aces. The order we choose them in doesn't matter, because remember, you can rearrange them in your hand and it's still the same set of aces. Well, the number of ways we can do this, how many aces do we have to choose from? Well, we have 4 to choose from, and we're choosing 3 out of the 4. So it's going to be 4, combination 3. If you do this one in your calculator, you'll come out with a total of 4. So there's 4 different ways to choose specifically 3 aces. And again, to guarantee you're getting aces, you're only choosing aces from other aces. You're throwing away the rest of the cards in the deck. Now, step 2 in our process is to choose our 2 kings. We have 4 kings to choose from, and we're choosing 2 of them. Again, it's a combination because the order doesn't matter. We rearrange the kings and it's the same set of kings. It's the same hand of cards. So 4 combination 2 comes out to 6. So there's 4 ways to do step 1, and then there's going to be 6 ways to do step 2. So in order to perform our 2 steps in the process, we multiply the total number of ways together. So 4 times 6 is going to give us 24. So there are 24 hands of cards in total that specifically have 3 aces and 2 kings, 24 hands in total. Okay, let's look at another situation. Now instead of 5 cards, we have 6 cards. So how many 6-card hands consist entirely of clubs? Again, we're looking at a combination. We rearrange the cards in our hand and it's still the same hand of cards, so the order here is not going to matter, so it's going to be a combination. Now, we haven't broken it down. Notice we want a hand that's just clubs. So all we're doing is choosing clubs. It's similar to the situation before, but rather than thinking of the cards fitting into two separate categories and we're choosing each type of card individually, now we're just choosing cards from one category. We're choosing cards that have to be clubs. Well, what's the only way you can make sure you get all clubs? You'd have to throw away your spades, your hearts, and your diamonds and just choose from the set of clubs. Well, if you were to do that, how many clubs do you have to choose from? Clubs is going to be one suit, so you have 13 cards in that particular suit. So there's only one operation. The single operation is choosing your 6 clubs. You have 13 to choose from, and then you're choosing 6. So 13 combination 6 comes out to 1,716. Now keep in mind, this was not dependent on us using clubs. It was dependent on us choosing just from one suit. So if this had been spades or hearts or diamonds, it would have been the exact same outcome. It's the fact that we're restricting the deck in this particular way so that we're only choosing from the set of clubs. Okay, let's look at another one. How many 7 card hands consist of 3 hearts and 4 diamonds? Okay, this is also going to be a combination. Order doesn't matter. We're choosing based on restrictions at this point. So we have to choose hearts, 3 hearts specifically, and then diamonds, 4 diamonds specifically. Just like with the aces and kings, we'd have to break this down. Think of this as 2 steps. Step 1 is choosing the hearts, and step 4 is choosing the diamonds. So imagine throwing away the rest of the deck and then organizing the hearts in one pile, organizing the diamonds in another pile. So there would be 13 cards in pile 1, 13 cards in pile 2. So operation 1 is choose the 3 hearts from the pile of hearts. Well, we have 13 to choose from, and we're choosing 3 for a total of 286 different combinations. For the diamonds, we're choosing 4. So we have 13 diamonds, and from that, we're choosing 4 for a total of 715 different combinations. Step 1, there's 286 ways to do that. And then step 2, there's 715 ways to do that. So we take the product of those 2 numbers, representing how many ways we can perform each step, and that's going to be 204,490. Okay. Let's look at one last cards example. This one's going to be slightly different, but again, we just have to think in terms of what are the actual choices being made, what are the operations we're taking, and then how many ways can we do each operation. So we're going to go back to a 3-card hand. We'll keep it small. Here's the question. How many 3-card hands have all cards from the same suit? In other words, all spades, all clubs, all hearts, or all diamonds. We don't know which one it is, but we just want to know how many hands are going to have specifically all cards of one particular suit. Well, again, we're talking about cards. It's going to be a combination. Order that we get them in doesn't matter. We can rearrange the cards in our hands, and it's still going to be the same thing. Now, what are the operations here, though, if you think about what's actually happening in order to choose all cards from the same suit? Well, number 1, you'd have to know what suit are we going with. Are we going with spades? Are we going with clubs? Are we going with hearts or diamonds? So operation 1 is choose the suit. Choose the suit that we're going to deal from. The only way you could make sure that you got cards that were all the same suit is to separate all the suits out and only deal from one pack representing one suit. But we need to know which pack are we going to choose. So we split that deck, that 52 card deck, up into 4 piles, one for each individual suit. So we have 4 suits to choose from, and we're choosing one of them in order to know which pile to deal from. So for combination 1, there's going to be 4 different ways to choose. Well, that makes sense. If there's 4 suits and we're choosing a suit, we have 4 different things we can choose from. Okay. Now, once we've chosen our suit, now we're choosing the 3 cards. So picture 4 packs of cards. We've chosen the one we want, the rest of them get thrown away. We're now choosing from that one pack of cards representative of the suit we just chose. So from that pack, we're going to deal 3 cards. Well, each of those individual packs, now we only have one of them, has 13 cards because it's all the cards in a particular suit. So we have 13 to choose from, and then we're choosing 3 for a total of 286 combinations. So 4 choices for the first operation when we choose our suit, when we choose which of the 4 piles we're going to deal from, and then 286 options to choose the 3 cards from that pile. So 4 times 286 is going to be 1,144. So that's going to be the number of hands that look like that. Notice that number, for instance, is substantially smaller than the number in the previous situation. That's because we had a very, very strong restriction in this situation. Choosing all cards from the same suit is much stricter than choosing 3 hearts and 4 diamonds, in which there's a combination of different cards. Not only do we have more cards here, but we have fewer restrictions overall than saying we have to have the same suit of cards. So automatically, there are fewer ways to do this particular problem than there would be other types of problems that also involve cards. Okay, let's take a step away from cards. Let's look at another situation. Serial numbers. So serial numbers for a product are made using 2 letters followed by 3 numbers. So it's going to be 5 elements, 2 letters first, and then 3 numbers after that. If the letters are taken from the first 8 letters of the alphabet with no repeats, and the numbers are taken from the 10 digits, 0 to 9, with no repeats, how many serial numbers are possible? Well, this is definitely going to be a permutation. If we rearrange the same letters and the same numbers, we get a different serial number. So because arrangement is involved here, changing the order changes the actual outcome, we know this is going to be a permutation. Now we're choosing letters and we're choosing numbers, so we have to make those individual choices separately. We can't throw all the letters and all the numbers into a big pile and then just choose at random, because we can't guarantee we're going to get the sequence that we need that has 2 letters first and then 3 letters second. So we break it down into 2 steps. So operation 1 is choose the 2 letters, and then operation 2 is choose the 3 numbers. Now we've been told that there are no repeats allowed. So once we use a letter, we use it up. Once we use a number, we use it up. So we can use the permutation formula, just recognizing how many we have to choose from and how many we're choosing out of that group. So let's start with the letters. We have the first 8 letters of the alphabet. So we have 8 to choose from. Well, how many are we choosing? Our serial number has 5 parts and it starts with 2 letters. So we have 8 letters to choose from, and we're choosing 2, and it's a permutation because the order matters. So AB and then BA would be considered different permutations. The order changes the serial number, so the order matters. So 8 permutation 2 is going to be 56. So there's 56 ways to choose the 2 letters at the beginning of the serial number. Now step 2, choose the 3 numbers. We have the 10 digits to choose from. And again, no repeats are allowed. So we have 10 to choose from, and we're choosing 3 out of the 10, and it's a permutation because there's no repeats and because the order matters. So 0, 1, 2, 2, 1, 0, 1, 0, 2, all different outcomes. So 10 permutation 3, 720 ways to choose our numbers. So 56 ways to do step 1, 720 ways to do step 2, multiply them together, that's going to be 40,320. So that's the number of different serial numbers we could create that look like this. Imagine if you have a serial number that's like 16 digits, think like a credit card number. How many different possibilities are there for credit card numbers? Well, in that case, we also can repeat digits, so there's some other situations involved. How the credit card number starts has a lot to do with the provider you have, if it's Visa, if it's MasterCard. But in general, imagine taking 16 digits. Automatically, this total expands quite a bit. So it's always kind of interesting to see how big the numbers get in these situations, especially when we're looking at a situation where it's permutations. Okay, let's look at a couple more problems. Okay. So a company has 7 senior officers and 5 junior officers. It wants to form a legislative committee. And how many ways can a 4-officer committee be formed so that it is composed of the following? Okay, so we're going to have some specific requirements on how the committee is formed, but the key word here is committee. We're looking at a group of even playing field people. We rearrange them at the table. It's the same group. The order they're in does not matter. We're just looking at a group of people that have been selected from a group at large. So automatically, we know it's going to be a combination. Regardless of the restrictions we impose, it's going to be a combination. So once we choose someone, we can't choose them again. But the order in which we choose the individuals does not matter. As long as it's the same group of people, it's the same combination. So let's start out with no restrictions. We can choose any 4 officers out of our group. So there's only one operation, just choose the 4 officers. Well, how many are in our group? We have 7 senior officers, we have 5 junior officers for a total of 12. Here, there are no restrictions. We can choose anyone we want out of the 12. So to choose our 4 officers, we have 12 to choose from, and then we're choosing 4. So 12 combination 4 comes out to 495. So 495 different choices if we can choose anyone in the group, no restrictions. So it doesn't matter whether they're a senior officer or a junior officer, we can choose anyone. Now, what if we specifically want to choose 4 senior officers? We want to choose the higher ranking individuals rather than choosing from the lower ranking individuals. Now, it's still only one operation because this group is homogeneous. There's no breakdown between one type of officer and then another type of officer. So we only have to make the one choice. We just have to make sure that we're only choosing from that group of senior officers. So now instead of having 12 to choose from, we can only choose from the 7 that represent senior officers. So 7, and we're choosing 4. So 7 combination 4, and that comes out to 35. Now again, it's not surprising that the number went down. There were no restrictions in situation A. In situation B, now we have a specific restriction. The more specific things become in general, the fewer combinations we have that match that particular situation. Now, what if we want 3 senior officers and 1 junior officer specifically? So that specific ratio, 3 to 1. Well, now we have to break it down and we have to do this in 2 steps. We've got to choose the senior officers from that group of 7. And then we have to choose the junior officer from that group of 5. If we were to throw them all into a pile and choose from the 12 at large, we can't guarantee that we're getting the ratio that we want. So we have to make these 2 choices separately. So operation 1 is choosing the 3 senior officers, and then operation 2 is choosing the junior officer. So to choose the senior officers, we have 7 to choose from, and we're choosing 3. So 7 combination 3 comes out to 35. For the junior officer, we have 5 to choose from. We're choosing 1. So 5 combination 1 comes out to 5. 35 ways to do step 1 multiplied by the 5 ways to do step 2 gives us 175 total combinations. So there are going to be 175 committees that consist of 3 senior officers and 1 junior officer. Now, what if it's an even split? What if we want 2 senior officers and 2 junior officers? Well, again, 2 steps in the process. Now we're choosing 2 senior officers and 2 junior officers, but again, the 2 sequences have to be separate. So choose directly from the seniors, choose directly from the juniors. So 7, and we're choosing 2, and then 5, and we're choosing 2. So 21 ways to do step 1. And then 10 ways to do step 2. 21 times 10 is going to give us 210 total possibilities. Okay, let's look at one final situation. We're going to have to be a little bit more creative here, but we can actually use some of the information we already have. So the last possibility is that we want to choose at least 2 senior officers. Not necessarily exactly, but at least 2 senior officers. Well, first thing we need to do is we need to think about all the different ways this could look, because at least is not specific. It says we can take on a variety of different outcomes as long as we have at least 2 senior officers. Well, we know we're picking 4 officers in total, so that's going to limit our possibilities. So at least 2 senior officers. Well, we could have exactly 2, that's a possibility. If we have exactly 2 senior officers, then we have to also have 2 junior officers, okay, in order to have the committee of 4. Now, at least means we could have more than this total, we just can't have less than. So we could have 3 senior officers, and then the 4th one is a junior officer. That's a possibility. And then the only other possibility that would meet this requirement is that we have a committee of all senior officers. Well, I worked these out again, but notice those are the 3 situations we just looked at. 2 senior officers and 2 junior officers, 3 senior officers and 1 junior officer, and then 4 senior officers in total. So we've already worked those out ahead of time, but say you hadn't. You break it down and you do it the same way. So this is a sequence of 2 operations. How many ways can you do step 1? Well, you're choosing 2 out of the 7. How many ways can you do step 2? Well, you're choosing 2 out of the 5. Multiply the number of ways you do each step together. Operation 1, choose 3 out of the 7. Operation 2, choose 1 out of the 5. Same idea, multiply those together. And then for the last one, because there's only one choice to make, we only have one option for our combination. So we're choosing 4 out of the 7 for a total of 35. Now, what we do at this point, we're going to have to be careful about. This is not a sequence of 3 big steps. This is one possibility. This gives us some of the combinations we could have. This is another possibility. It gives us some more of the possibilities we could have. And this is the last possibility, and it gives us the rest of the combinations we could have. So we have a total of 210, a total of 175, and then a total of 35. We're not going to multiply those together though. By multiplying them together, we're saying take these 3 steps and think of these as 3 steps in one big process. That's not what's going on here. We made the choices in terms of process for each of 3 different possibilities. This is one possibility that gives us some of the possible outcomes, and these are the other possibilities that also give us some of the outcomes. So what we want to do is add up these outcomes. These are subtotals that represent different ways we could come out with a situation representative of at least 2 senior officers. So 210 come from this combination, 175 come from this combination, and then the remaining 35 come from the last combination for a total of 420. So again, why did we not multiply these together? Multiplication implies that we're doing all 3 things at the same time. We're making these choices at the same time. We're choosing 2 seniors and 2 juniors at the same time, and somehow these go together. That's when we multiply. Each of these different subtotals comes from one different combination of choices. We make one different combination of choices that fits under this particular category of restricted choices. Each of these subtotals is one different way we could come up with some combination that meets our requirements. So in this case, we're just adding up those subtotals, and that gives us a total of 420. So permutation and combination problems, we can get a variety of different problems. A bunch of different situations can actually mirror the situations that in general we represent as permutations and combinations. So again, start by determining what situation are you in. If the order matters, then we're talking about a permutation. If rearrangement doesn't change anything, then we're talking about a combination. Then you're looking for how many am I choosing from, and how many of that group am I choosing. That's going to be your values for N and R, and you use your calculator from there. As we've seen in a problem like this, sometimes it's going to be steps within the problem. So if we're making different choices from different categories, think about making different choices from different categories. You have to represent each type of choice as an individual operation. So choosing from one category, you make the choice strictly from that category. That's going to be one operation. Choosing from another category, you choose strictly from that category. That's going to be another operation. So sometimes it's going to be combinations and permutations within the context of another problem, and then you just multiply together the number of outcomes, and that's going to give you your actual total.